Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 121, Forecasting Transformative AI Timelines Using Biological Anchors, published on the 14th of October 2020 by Rohin Shah. Link, Draft Report on AI Timelines by Ajay Kotra, summarized by Rohin. Once again, we have a piece of work so large and detailed that I need a whole newsletter to summarize it. This time, it's a quantitative model for forecasting when transformative AI will happen. Note that since this is still a draft report, the numbers are in flux. The numbers below were taken when I read it and may no longer be up to date. The overall framework. The key assumption behind this model is that if we train a neural net or other ML model that uses about as much computation as the human brain, that will likely result in transformative AI, abbreviated TAI. Defined as AI that has an impact comparable to that of the Industrial Revolution. In other words, we anchor our estimate of the ML model's inference computation to that of the human brain. This assumption allows us to estimate how much compute will be required to train such a model using 2020 algorithms. By incorporating a trend extrapolation of how algorithmic progress will reduce the required amount of compute, we can get a prediction of how much compute would be required for the final training run of a transformative model in any given year. We can also get a prediction of how much compute will be available by predicting the cost of compute in a given year, which we have a decent amount of past evidence about, and predicting the maximum amount of money an actor would be willing to spend on a single training run. The probability that we can train a transformative model in year Y is then just the probability that the compute requirement for year Y is less than the compute available in year Y. The vast majority of the report is focused on estimating the amount of compute required to train a transformative model using 2020 algorithms, where most of our uncertainty would come from. The remaining factors are estimated relatively quickly without too much detail. I'll start with those so that you can have them as background knowledge before we delve into the real meat of the report. These are usually modeled as logistic curves in log space. That is, they're modeled as improving at some constant rate, but will level off and saturate at some maximum value after which they won't improve. Algorithmic progress. First off, we have the impact of algorithmic progress. The OpenAI blog post AI and Efficiency, discussed in newsletter 99, estimates that algorithms improve enough to cut compute times in half every 16 months. However, this was measured on ImageNet, where researchers are directly optimizing for reduced computation costs. It seems less likely that researchers are doing as good a job on reducing computation costs for training a transformative model, and so the author increases the halving time to 2 to 3 years, with a maximum of somewhere between 1 to 5 orders of magnitude, with the assumption that the higher the technical difficulty of the problem, the more algorithmic progress is possible. Cost of compute. Second, we need to estimate a trend for compute costs. There's been some prior work on this, summarized in newsletter 97. The report has some similar analyses, and ends up estimating a doubling time of 2.5 years, and a very unstable maximum of improvement by a factor of 2 million in 2100. Willingness to spend. Third, we would like to know the maximum amount, in 2020 dollars, any actor might spend on a single training run. Note that we're estimating the money spent on a final training run, which doesn't include the cost of initial experiments or the cost of researcher time. Currently, the author estimates that all-in project costs are 10 to 100 times larger than the final training run cost, but this will likely go down to something like 2 to 10 times as the incentive for reducing this ratio becomes much larger. The author estimates that the most expensive run in a published paper was the final training run of AlphaStar from newsletter 43 at about 1 times 10 to the 23 flop and $1 million cost. However, there have probably been unpublished results that are slightly more expensive, maybe $2 to $8 million. In line with AI and compute, discussed in newsletter 7, this will probably increase dramatically to about $1 billion in 2025. Given that AI companies each have around $100 billion cash on hand, and could potentially borrow additional several hundreds of billions of dollars, given their current market caps and likely growth in the worlds where AI still looks promising, it seems likely that low hundreds of billions of dollars could be spent on a single run by 2040, corresponding to a doubling time from $1 billion in 2025 of about 2 years. To estimate the maximum here, we can compare to megaprojects like the Manhattan Project or the Apollo program, which suggests that a government could spend around 0.75% of GDP for about 4 years. Since transformative AI will likely be more valuable economically and strategically than these previous programs, we can shade that upwards to 1% of GDP for 5 years. Assuming all-in costs are 5 times that of the final training run, this suggests the maximum willingness to spend should be 1% of GDP for the largest country, which we assume grows at 3% every year. Strategy for estimating training compute for a transformative model. In addition to the 3 factors of algorithmic progress, cost of compute, and willingness to spend, we need an estimate of how much computation would be needed to train a transformative model using 2020 algorithms, which I'll discuss next. Then, at year Y, the compute required is given by computation needed with 2020 algorithms times improvement factor from algorithmic progress, which in this report is a probability distribution. At year Y, the compute available is given by flop per dollar, aka compute cost, times money that can be spent, which in this report is a point estimate. We can then simply read off the probability that the compute required is greater than the compute available. Okay, so the last thing we need is a distribution over the amount of computation that would be needed to train a transformative model using 2020 algorithms, which is the main focus of this report. There's a lot of detail here that I'm going to elide over, especially in talking about the distribution as a whole, whereas I will focus primarily on the median case for simplicity. As I mentioned early on, the key hypothesis is that we'll need to train a neural net or other ML model that uses about as much compute as a human brain. So the strategy will be to first translate from compute of human brain to inference compute of neural net, and then to translate from inference compute of neural net to training compute of neural net. How much inference compute would a transformative model use? We can talk about the rate at which synapses fire in the human brain. How can we convert this to flop? The author proposes the following hypothetical. Suppose we redo evolutionary history, but in every animal we replace each neuron with n floating point units that each perform 1 flop per second. For what value of n do we still get roughly human-level intelligence over a similar evolutionary timescale? The author then does some calculations about simulating synapses with flops, drawing heavily on the recent report on brain computation discussed in newsletter 118, to estimate that n would be around 1 to 10,000, after which some more calculations suggest that the human brain is doing the equivalent of 1 times 10 to the 13 to 1 times 10 to the 16 flop per second, with a median of 1 times 10 to the 15 flop per second, and a long tail to the right. Does this mean we can say that a transformative model will use 1 times 10 to the 15 flop per second during inference? Such a model would have a clear flaw. Even though we're assuming that algorithmic progress reduces compute costs over time, if we did the same analysis in, for example, 1980, we'd get the same estimate for the compute cost of a transformative model, which would imply that there was no algorithmic progress between 1980 and 2020. The problem is that we'd always estimate the brain as using 1 times 10 to the 15 flop per second, or around there, but for our ML models, there's a difference between a flop per second using 2020 algorithms and a flop per second using 1980 algorithms. How do we convert from brain flop per second to inference flop per second for 2020 ML algorithms? One approach is to look at how other machines we've designed compare to the corresponding machines that evolution has designed. An analysis by Paul Cristiano concluded that human-designed artifacts tend to be 2 to 3 orders of magnitude worse than those designed by evolution when considering energy usage. Presumably a similar analysis done in the past would have resulted in higher numbers and thus wouldn't fall prey to the problem above. Another approach is to compare existing ML models to animals with a similar amount of computation and see which one is subjectively more impressive. For example, the AlphaStar model uses about as much computation as a bee brain, and large language models use somewhat more. The author finds it reasonable to say that AlphaStar is about as sophisticated as a bee, or that GPT-3 from newsletter 102 is more sophisticated than a bee. We can also look at some abstract considerations. Natural selection had a lot of time to optimize brains, and natural artifacts are usually quite impressive. On the other hand, human designers have the benefit of intelligent design and can copy the patterns that natural selection has come up with. Overall, these considerations roughly balance each other out. Another important consideration is that we're only predicting what would be needed for a model that was good at most tasks that a human would currently be good at. Think a virtual personal assistant, whereas evolution optimized for a whole bunch of other skills that were needed in the ancestral environment. The author subjectively guesses that this should reduce our estimate of compute costs by about an order of magnitude. Overall, putting all these considerations together, the author intuitively guesses that to convert from brain flop per second to inference flop per second for 2020 ML algorithms, we should add an order of magnitude to the median, and add another 2 orders of magnitude to the standard deviation to account for our large uncertainty. This results in a median of 1 times 10 to the 6 flop per second for the inference time compute of a transformative model. Training compute for a transformative model. We might expect a transformative model to run a forward pass 0.1 to 10 times per second, which on the high end would match human reaction time of 100 milliseconds, and for each parameter of the neural net to contribute 1 to 100 flop per forward pass, which implies that if the inference time compute is 1 times 10 to the 16 flop per second, then the model should have 1 times 10 to the 13 to 1 times 10 to the 17 parameters, with a median of 3 times 10 to the 14 parameters. We now need to estimate how much compute it takes to train a transformative model with 3 times 10 to the 14 parameters. We assume this is dominated by the number of times you have to run the model during training, or equivalently, the number of data points you train on times the number of times you train on each data point. In particular, this assumes that the cost of acquiring data is negligible in comparison. The report argues for this assumption. For the sake of brevity, I won't summarize it here. For this, we need a relationship between parameters and data points, which we'll assume will follow a power law of k p to the alpha, where p is the number of parameters and k and alpha are constants. A large number of ML theory results imply that the number of data points needed to reach a specified level of accuracy grows linearly with the number of parameters, i.e. alpha equals 1, which we can take as a week prior. We can then update this with empirical evidence from papers. Scaling laws for neural language models, discussed in Newsletter 87, suggests that for language models, data requirements scale as alpha equals 0.37 or as alpha equals 0.74, depending on what measure you look at. Meanwhile, another paper, Deep Learning Scaling is Predictable Empirically, suggests that alpha equals 1.39 for a wide variety of supervised learning problems, including language modeling. However, the former paper studies a more relevant setting. It includes regularization and asks about the number of data points needed to reach a target accuracy, whereas the latter paper ignores regularization and asks about the minimum number of data points that the model cannot overfit to. So overall, the author puts more weight on the former paper and estimates a median of alpha equals 0.8, though with substantial uncertainty. We also need to estimate how many epochs will be needed, i.e. how many times we train on any given data point. The author decides not to explicitly model this factor, since it will likely be close to 1, and instead lumps in the uncertainty over the number of epochs with the uncertainty over the constant factor in the scaling law above. We can then look at language model runs to estimate a scaling law for them, for which the median scaling law predicts that we would need 1 times 10 to the 13 data points for our 3 times 10 to the 14 parameter model. However, this has all been for supervised learning. It seems plausible that a transformative task would have to be trained using RL, where the model acts over a sequence of time steps and then receives non-differentiable feedback at the end of those time steps. How would scaling laws apply in this setting? One simple assumption is to say that each rollout over the effective horizon counts as one piece of meaningful feedback, and so should count as a single data point. Here, the effective horizon is the minimum of the actual horizon and 1 over 1 minus gamma, where gamma is the discount factor. We assume that the scaling law stays the same. If we instead try to estimate it from different RL runs, it can change the results by about 1 order of magnitude. So we now know we need to train a 3 times 10 to the 14 parameter model with 1 times 10 to the 13 data points for a transformative task. This gets us nearly all the way to the compute required with 2020 algorithms. We have an approximately 3 times 10 to the 14 parameter model that takes approximately 1 times 10 to the 16 flop per forward pass, that's trained on about 1 times 10 to the 13 data points, with each data point taking h time steps, for a total of h times 1 times 10 to the 29 flop. The author's distributions are centered at h times 10 to the 30 flop. I suspect this is simply because the author was computing with distributions, whereas I've been directly manipulating medians in this summary. The last and most uncertain piece of information is the effective horizon of a transformative task. We could imagine something as low as 1 subjective second for something like language modeling, or something as high as 1 times 10 to the 9 subjective seconds, i.e. 32 subjective years, if we were to redo evolution, or train on a task like do effective scientific research and development. The author splits this up into short, medium, and long horizon neural net paths, corresponding to horizons of 1 times 10 to the 0 to 1 times 10 to the 3, 1 times 10 to the 3 to 1 times 10 to the 6, and 1 times 10 to the 6 to 1 times 10 to the 9, respectively, and invites readers to place their own weights on each of the possible paths. There are many important considerations here. For example, if you think that the dominating cost will be generative modeling, GPT-3 style, but maybe also for images, video, etc., then you would place more weight on short horizons. Conversely, if you think the hard challenge is to gain meta-learning abilities, and that we probably need data points comparable to the time between generations in human evolution, then you would place more weight on longer horizons. Adding 3 more potential anchors. We can now combine all these ingredients to get a forecast for when compute will be available to develop a transformative model. But not yet. We'll first add a few more possible anchors for the amount of computation needed for a transformative model. All of the modeling so far has anchored the inference time computation of a transformative model to the inference time computation of the human brain. First, we can anchor parameter count of a transformative model to the parameter count of the human genome, which has far fewer parameters than the human brain. Specifically, we assume that all the scaling laws remain the same, but that a transformative model will only require 7.5 times 10 to the 8 parameters, the amount of information in the human genome, rather than our previous estimate of 1 times 10 to the 15 parameters. This dramatically reduces the amount of computation required, though it's still slightly above that of the short horizon neural net, because the author assumed that the horizon for this path was somewhere between 1 and 32 years. Second, we can anchor training compute for a transformative model to the compute used by the human brain over a lifetime. As you might imagine, this leads to a much smaller estimate. The brain uses about 1 times 10 to the 24 flop over 32 years of life, which is only 10 times the amount used for AlphaStar, and even after adjusting upwards to account for man-made artifacts being worse than those made by evolution, the resulting model predicts a significant probability that we would already have been able to build a transformative model. Finally, we can anchor training compute for a transformative model to the compute used by all animal brains over the course of evolution. The basic assumption here is that our optimization algorithms and architectures are not much better than simply redoing natural selection from a very primitive starting point. This leads to an estimate of about 1 times 10 to the 41 flop to train a transformative model, which is more than the long horizon neural net path, though not hugely more. Putting it all together. So we now have 6 different paths: the 3 neural net anchors, short, medium, and long horizon, the genome anchor, the lifetime anchor, and the evolution anchor. We can now assign weights to each of these paths, where each weight can be interpreted as the probability that that path is the cheapest way to get a transformative model, as well as a final weight that describes the chance that none of the paths work out. The long horizon neural net path can be thought of as a conservative default view. It could work out simply by training directly on examples of a long horizon task where each data point takes around a subjective year to generate. However, there are several reasons to think that researchers will be able to do better than this. As a result, the author assigns 20% to the short horizon neural net, 30% to the medium horizon neural net, and 15% to the long horizon neural net. The lifetime anchor would suggest that we either already could get TAI or are very close, which seems very unlikely given the lack of major economic applications of neural nets so far, and so gets assigned only 5%. The genome path gets 10%, the evolution anchor gets 10%, and the remaining 10% is assigned to none of the paths working out. This predicts a median of 2052 for the year in which some actor would be willing and able to train a single transformative model, with the full graphs shown in the newsletter. This is the first time that the newsletter has featured graphs, which is really going to strain my pronunciation. Suffice it to say there are 2 graphs. One is the probability that flop to train a transformative model is affordable by year Y, which has years on the x-axis and cumulative probability on the y-axis, and then the 6 different anchors shown as lines, with a line for the weighted average as well. And yes, the weighted average passes 0.5 between 2050 and 2055. And the second graph is probability that flop to train a transformative model is first affordable in year Y, which has, again, year on the x-axis and probability in this year on the y-axis. And it shows the distribution of those probabilities and also the contributions for each year from each of the anchors. That seems to peak at 2040. How does this relate to TAI? Note that what we've modelled so far is the probability that by year Y we will have enough compute for the final training run of a transformative model. This is not the same thing as the probability of developing TAI. There are several reasons that TAI could be developed later than the given prediction. 1. Compute isn't the only input required. We also need data, environments, human feedback, etc. While the author expects that these will not be the bottleneck, this is far from a certainty. 2. When thinking about any particular path and making it more concrete, a host of problems tend to show up that will need to be solved and may add extra time. Some examples include robustness, reliability, possible breakdown of the scaling laws, the need to generate lots of different kinds of data, etc. 3. AI research could stall, whether because of regulation, a global catastrophe, an AI winter, or something else. However, there are also compelling reasons to expect TAI to arrive earlier. 1. We may develop TAI through some other cheaper route, such as a services model, as discussed in Newsletter 40. 2. Our forecasts apply to a balanced model that has a similar profile of abilities to a human. In practice, it will likely be easier and cheaper to build an unbalanced model that's superhuman in some domains and subhuman in others, that is nonetheless transformative. 3. The curves for several factors assume some maximum after which progress is not possible. In reality, it's more likely that progress slows to some lower but non-zero growth rate. In the near future, it seems likely that it would be harder to find cheaper routes, since there's less time to do the research, so we should probably assume that the probabilities are overestimates, and for similar reasons for later years, the probabilities should be treated as underestimates. For the median of 2052, the author guesses that these considerations roughly cancel out, and so rounds the median for development of TAI to 2050. A sensitivity analysis concludes that 2040 is the most aggressive plausible median, while the most conservative plausible median is 2080. Rohin's opinion. I really like this report. It's extremely thorough and anticipates and responds to a large number of potential reactions. I've made my own timelines estimate using the provided spreadsheet and have adopted the resulting graph with a few modifications as my TAI timeline, which ends up with a median of around 2055. This is saying quite a lot. It's pretty rare that a quantitative model is compelling enough that I'm inclined to only slightly edit its output, as opposed to simply using the quantitative model to inform my intuitions. Here are the main ways in which my model is different from the one in the report. 1. Ignoring the genome anchor. I ignore the genome anchor because I don't buy the model. Even if researchers did create a very parameter-efficient model class, which seems unlikely, I would not expect the same scaling laws to apply to that model class. The report mentions that you could also interpret the genome anchor as simply providing a constraint on how many data points are needed to train long-horizon behaviors, since that's what evolution was optimizing. But I prefer to take this as fairly weak evidence that informs what weights to place on short versus medium versus long horizons for neural nets. 2. Placing more weight on short and medium horizons relative to long horizons. I place 30% on short horizons, 40% on medium horizons, and 10% on long horizons. The report already names several reasons why we might expect the long horizon assumption to be too conservative. I agree with all of those and have one more of my own. If meta-learning turns out to require a huge amount of compute, we can instead directly train on some transformative task with a lower horizon. Even some of the hardest tasks, like scientific R&D, shouldn't have a huge horizon. Even if we assume that it takes human scientists a year to produce the equivalent of a single data point, at 40 hours a week, that comes out to a horizon of 2,000 subjective hours, or 7 times 10 to the 6 seconds. This is near the beginning of the long horizon realm of 1 times 10 to the 6 to 1 times 10 to the 9 seconds, and seems like a very conservative overestimate to me. Note that in practice, I'd guess we'll train something like a meta-learner, because I suspect the skill of meta-learning will not require such large average effective horizons. 3. Reduced willingness to spend. My willingness to spend forecasts are somewhat lower. The predictions and reasoning in this report feel close to upper bounds on how much people might spend, rather than predictions of how much they will spend. Assuming we reduce the ratio of all-in project costs to final training run costs to 10 times, spending $1 billion on a training run by 2025 would imply all-in project costs of $10 billion, which is about 40% of Google's yearly R&D budget of $26 billion, or 10% of the budget for a 4-year project. Possibly this wouldn't be classified as R&D, but it would also be 2% of all expenditures over 4 years. This feels remarkably high to me for something that's supposed to happen within 5 years. While I wouldn't rule it out, it wouldn't be my median prediction. 4. Accounting for challenges. While the report does talk about challenges in, for example, getting the right data and environments by the right time, I think there are a bunch of other challenges as well. For example, you need to ensure that your model is aligned, robust, and reliable, at least if you want to deploy it and get economic value from it. I do expect that these challenges will be easier than they are today, partly because more research will have been done, and partly because the models themselves will be more capable. Another example of a challenge would be PR concerns. It seems very plausible to me that there will be a backlash against transformative AI systems that results in those systems being deployed later than we'd expect them to be according to this model. To be more concrete, if we ignore points 1 to 3 and assume this is my only disagreement, then for the median of 2052, rather than assuming that reasons for optimism and pessimism approximately cancel out to yield 2050 as the median for TAI, I'd be inclined to shade upwards to 2025 or 2060 as my median for TAI. This concludes Alignment Newsletter number 121. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.